Hi, my name is Alvin. Today I'm going to present to you an interesting topic, which is interesting implementations of parallel computing in some algorithms. I'm going to present this to you with my two other teammates, Tianyo and Trinling Kia. Initially, computer software is written for serial computation, and this means instructions are executed serially one by one. This can prove to be slow when it comes to a bigger and much more complex problems, and this shows that there is a need of a new way to compute and solve problems. So then people comes up with an idea of doing things in parallel. So let's compare between the serial and parallel computing. In serial, only one instruction can be executed at one time, and this means that serial computing is pretty slow when it comes to solving big problems. Whereas in parallel, they are able to execute more than one instruction at one time, and that means the problem can be divided into several smaller problems, then executed together, thus making it faster in solving problems. However, due to the nature of it, it needs more processors to run, and it is more complex to be implemented. So now, let's have a look at several implementations of parallel computing in some algorithms. First of all, it is the famous Dijkstra algorithm. Dijkstra algorithm is an algorithm discovered to solve the problem of finding the shortest path from a point to a destination. It is used in network routing protocols such as OSPF protocol. So how does it work? Well, let's take a look at this diagram. Our source node will be A and our destination will be G. So we start at node A. What A knows is that the path to the rest of them is initially infinity and the value of itself is 0. Next, it will check the neighbors. First of all, it will check on B's value by adding its own value with the length to node B, which is 1, and therefore the value of B will be 1. The same goes for C, in which its value is going to be 2. We find the most minimum value out of the visited neighbors and put it into the clusters. Then again, all nodes in the cluster will check against the neighbors that is not in the cluster. Example, B will check against E and D, and A will check against C again. And then it will grab the most value and put them into the clusters. Keep doing it and it will know which path that it takes to reach the destination. So what happens when the network gets bigger? Well, with this serial Dijkstra algorithm, it will take very long for a node to find its shortest path to a destination. This is one of the ways to perform parallel Dijkstra algorithm. Firstly, each of the processor will identify the closest node to the source node, and then each of them performs parallel prefix to choose the closest node, and then each of them broadcasts the result to all other processors, and finally each processor updates its cluster. Look at this routing table of A. Assuming we have 3 cores, and each of them takes some node as their subsets. The green one consists of B and C, and the purple gets D and E, and the yellow gets F and G. They will then perform the steps that I have just mentioned in parallel, and broadcast their information to each other. In this short diagram, it may not look as fast as it seems. However, in a bigger network, this can perform much faster than a normal Dijkstra algorithm. So let's take a look at the performance of both serial and parallel Dijkstra algorithm. For serial Dijkstra algorithm, it takes O(n) squared, while for parallel Dijkstra algorithm, it takes O(n) squared divided by P plus n times log P, where P is the number of processors. We can see that if there is an increased number of processors, then the performance of parallel Dijkstra algorithm will be much better. It is interesting on how parallel method could be implemented in such an already complex algorithm and even improve its performance.
Monte Carlo algorithm. Monte Carlo algorithm. What's a Monte Carlo algorithm? Monte Carlo algorithms are both of class of computational algorithms that rely on the repeat random sampling to obtain the numerical result. For example, by running the simulation multi-solver in order to calculate those same probabilities, just like actual playing and recording result in real casino situation, hence the name. They are often using the physical and mathematical problems are most suited to applied when it's impossible to obtain the closed form expressions, or infeasible to apply the determined algorithms. Monte Carlo algorithms is a randomized algorithm that may produce an incorrect result, but with boundary probability. How the Monte Carlo algorithm works. Define a domain of possible inputs. Generate an input of random from a probability distribution over the domain. Perform deterministic computations on the inputs. Aggregate the result. Okay. We show an example how to use the Monte Carlo algorithm to estimate the value of pi. In the beginning, we see the pictures. After placing the more random points, the estimate of the pi is close to the actual value of the pi, 3.14. This is a mathematical expression of the Monte Carlo algorithm to estimate the value of the pi. Let's move to the pseudocode of the Monte Carlo algorithm, estimate of the value of pi. In the beginning, we create a random number of the generator. Second, each processor will run the number of the random walks. Then calculate the pi from each processor. That last, we output the result and the standard deviation sigma. Is a Monte Carlo algorithm suited to the parallel programming? All answer is yes. As the computer progresses from processor become cheaper and cheaper, it's great to have them compute together in the coordinate fashion. But the major issue in the parallel programming is that how to coordinate the communication between the various processors. Different processors have different speeds. Monte Carlo algorithm often proceed by averaging the large number of the computed value. It's straightforward to having the different processors calculate the different values, then using the appropriate average of this value to produce the final values. In that way, the communication between the processors is minimized, so the parallel programming is easy to facilitate. So we think the Monte Carlo algorithms are ideally suited to the parallel computing.
The next parallel implementation that we want to introduce is quicksort algorithm. At first, let's have a look at how quicksort algorithm works in a serial approach. We have a list of random unsorted numbers here. In this list, I choose 79, which is the first number, as pivot number. Actually, pivot number can be any number in the list. Next step, which we call partitioning. What happens here is all the numbers which is equal or smaller than pivot would go to the left array, and the bigger numbers will go to the right array, as you can see. Next, we will apply quick-sort algorithms recursively to left array first and followed by right array, and this is the order which program is executed. When the length of array is equal to 0 to 1, it will return itself. And final result will be the array, which is the combination of left array, pivot, and right array. And average complexity of this algorithm by serial approach is O(n) log n. And now we will look at how this algorithm is converted to parallel approach. Let's assume that we have 4 processes, P0 to P3. We take the previous list of random numbers, distribute those numbers equally to 4 processes. Our objective now is to redistribute those numbers in such a way that P0 will contain a list of numbers which is all smaller than P1s, and P1s smaller than P2, P2 smaller than P3. And how to achieve this? We choose a pivot from P0 and broadcast it to all other processes. We create a barrier to divide 4 processes in 2 groups. Upper group contain P0 and P1. Lower group contain P2 and P3. Number at 1 processes on upper group are exchanged to 1 processes on lower group. All numbers smaller than pivot will go to processes on upper group, and numbers higher than pivot will go to processes on lower group. In this example, P0 numbers are exchanged to P2s, and P1's numbers are exchanged to P3. After that, numbers are next exchanged among processes on the same group. For example, I choose a pivot on P0, and number higher than pivot will go to P1. Lower than pivot will go to P0. Same thing happened to P2 and P3. And now we have a list of processes which hold numbers that satisfy the condition we just set. Finally, we apply serial quick-sort algorithm to individual lists of numbers at each processes at the same time. And average time complexity is reduced to O(n) divided by P log n divided by P, while P is the number of processes. Next algorithm I want to introduce to you is a very famous algorithm, binary tree traversals. Let's see how it travels in a deep first serial approach. In a parallel approach, let's assume we have 4 processes represented by different colors in the side. First of all the processes will do the same task, which is travel through parent node until they reach the start node which they are supposed to travel separately. The fact that trees are comprised of independent subtrees makes parallelizing them very easily. Above are few examples of how traditional algorithm is converted to parallel approach. In the future, more and more algorithms will follow parallel approach as well. That's because every processor's architecture is now available in multi-core configuration, and moving forward, new tools, new programming model will be needed for programming in parallel environment. Thank you for listening.